Okay, welcome everybody for today's seminar class. I'm reporting from the classroom and we have a large crowd here gathered together for this exciting two papers back to back. The first paper is called TRRespass, and it has been a revolutionary paper since it was published last year in 2020. So Banu will present this paper, and just a quick introduction of Banu. Banu is a master's student, first year in the electrical engineering department, and she conducts research in Safari as well. And yeah, we are back to you, Banu.
Hi, Giray. Thanks for the introduction, and I will just present TRRespass, exploiting the main size of target row refresh. And I will just begin with the executive summary. Even though RowHammer is a serious problem, the current protection mechanisms rely on in-DRAM TRR mitigation, whose implementation details are unknown. The goal is to prove or disprove the security guarantees of in-DRAM TRR against RowHammer attacks. The methodology to analyze security of in-DRAM TRR is to perform a series of hammers and refreshes while varying the numbers. These experiments led to several key observations, such as the TRR mitigation present in DRAM modules acts on refresh command, and we can see how many aggressive rows TRR can detect by sweeping the number of refresh and aggressive rows. The authors proposed TRRespass, which is a black box test suite that automatically generates effective access patterns to bypass in-DRAM TRR mitigation mechanisms. The evaluations of TRRespass demonstrated its ability to create bit flips in 13 out of 42 DDR4 and LPDDR4 modules tested. Furthermore, these bit flips can be exploited to mount RowHammer attacks. The main key takeaway of the paper is that RowHammer is still an open problem, and we will see why it is still so. First, I will just provide some background for you. Here we see a typical organization of a DRAM. Memory controller communicates with the DRAM using the memory channel, and DRAM consists of several chips, which in turn consist of several banks. When memory controller wants to read something from memory, it should first activate the row that contains the data and bring it into the row buffer. The DRAM rows consist of DRAM cells, and basically each DRAM cell has two main elements: capacitor to encode the bit and an access transistor to access the bit. But the charge in the capacitor leaks over time. To ensure that we preserve the data correctly, DRAM rows are refreshed periodically, which restores the charge within the cells. And the phenomenon we want to investigate in this work is called RowHammer. Basically, it refers to the fact that if we repeatedly open and close a DRAM row, which is referred as hammering, we will get bit flips in the nearby cells. The rows that contain these cells with bit flips are called victim rows. There are some common hammering patterns. In the single-sided one, as you can see from the left figure, one aggressive row hammers the two nearby victim rows. In a double-sided case, two aggressive rows squeeze one victim row in the middle, which can cause more bit flips. One location, which is in the right of the figure, is similar to the single-sided as well. The difference is in the one location case, there's no additional aggressive rows. These three were the most common hammering patterns at that time. And when the authors tested 42 recent DDR4 modules against these patterns to understand the modern landscape, they observed no bit flips at all. Since these hammering patterns are capable of creating bit flips for DDR3 devices, this observation raises an important question. Is RowHammer a solved problem? Before we switch to the analysis of in-DRAM TRR, I would like to mention some of the prior proposals. The first, and an easy one, was to increase the refresh rate. But since the refresh rate needs to be increased significantly for current modules, this solution is not scalable. Another proposal is to isolate the victim rows from the aggressor rows by putting some additional isolation rows between them. This solution requires knowledge of in-DRAM row mapping, which is a proprietary information. So this is not feasible as well. Another proposal was to use error correcting codes to correct the bit flips, which in turn proved to be ineffective due to the large number of bit flips RowHammer attacks can create per cache line. One scalable and promising solution was proposed in the original RowHammer paper, which is PARA. Although this solution is the idea here is to flip a coin. Whenever a row is hammered, meaning accessed, and then with some small probability, refresh one of the nearby rows. And this solution is scalable and simple, but it does not provide deterministic security guarantees. These all are old mechanisms proposed, but they're not working because of the limitations I just explained. We will now see the effectiveness of current ones that seem to be effective for DDR4 modules. Returning back to our original question, is RowHammer solved with the in-DRAM TRR mitigations employed? A side note, when I talk about TRR, I am referring to a variety of solutions. What all these solutions have in common, though, they try to mitigate RowHammer by selectively refreshing the victim rows. The paper analyzes a variety of components with TRR implementations to develop a better understanding of the underlying TRR mechanism. Specifically, they analyze a TRR mechanism in memory controller and several TRR implementations inside the DRAM chips. And let's start with the memory controller part. It makes sense to mitigate RowHammer inside the memory controller, as the memory controller can monitor the number of activations to specific DRAM rows, and memory controllers can send additional refreshes to DRAM rows affected. But it has to know the maximum number of activations, referred to as MacValue in the presentation, that DRAM module can handle before a bit flip to be able to perform these actions mentioned. MacValue is written inside the SPD of the DRAM module as shown in the figure. Currently, we may have three different such MacValues in the memory modules. The first one is unlimited, to mean that this memory module is RowHammer free. The second one is untested, and the last one is a discrete value to describe the actual number of activations the DRAM module can bear. This paper focuses on Intel PTRR implementation specifically in order to verify the existence of PTRR and understand its deployment in Intel systems as well as its effectiveness. The main motivation to focus on Intel's PTRR implementation is that PTRR is the most leading defense mechanism employed inside a memory controller. And also the underlying implementation is not well known. According to Intel's public documentation, PTRR refreshes a victim row when the number of hammers to an aggressor row exceeds the MacValue of the memory module. Also for the non-TRR compliant modules, meaning modules without the MacValue or modules with MacValue set to untested, it just doubles the refresh rate. Experiments are conducted with this Intel Xeon device, which is officially reported to support PTRR. In the first experiment, the MacValue is overwritten to untested just to simulate a non-TRR compliant DRAM module. And indeed, refresh rate is doubled, as we can see from the orange and blue lines we have in the figure. In the second experiment, the MacValue is written to a discrete value and to unlimited. As you can see in the left figure, we observe that the number of bit flips drastically decreases when PTRR is enabled, and it's enabled when MacValue set is set to 400K in the orange bar. However, in the right, same number of bit flips observed. So for some systems, overwriting the MacValue to untested or to different discrete values do not change the refresh rate or bit flips observed. And this table gives the list of systems tested, and we can see that PTRR is only employed in one of the CPUs tested. I think here the key takeaway is RowHammer mitigation entirely relies on undocumented in-DRAM TRR implementations. So let's talk about in-DRAM TRR mitigation mechanisms now and try to understand their underlying implementations. DRAM vendors have not publicly shared the details of exact RowHammer protection mechanisms they implement in the form of TRR. And the goal here is that to learn these details by reverse engineering it. And for that, the authors utilize an open source FPGA memory controller, SoftMC, to perform this task. And here is the methodology they followed. And we will start with creating some hypotheses. We know that TRR is an umbrella term, but there are two requirements for supporting TRR. The first requirement is the existence of a sampler which tracks aggressor row activations in turn to identify the victim rows. And the hypothesis we have regarding the sampler is its size is limited, which implies that TRR mitigation can protect a limited number of victim rows. The second requirement is the existence of an inhibitor, which is responsible for mitigating the hammering process, and an effective solution is generating extra refreshes for these victim rows identified. The hypothesis we have for the inhibitor is that it acts on a refresh command. So here again, only a limited number of victim rows can be refreshed when inhibitor acts due to the DRAM timing parameters we have. And this limited number is going to be an important factor while trying to reverse engineer the in-DRAM TRR mechanisms. Now we will identify our goals and we will see which question we would like to answer. The goal is to answer the following questions about the in-DRAM TRR mitigation mechanisms. What is the size of the sampler? How does the sampler check aggressive rows? For example, does it record row activation commands at a constant frequency or based on a function of time? How does the inhibitor work? And more importantly, can it prevent bit flips? Now I will talk about some of the case studies to answer these previous questions. The first question to ask is, how many activations we need to cause bit flips in DDR4 modules? To find out that, we will disable the refresh command and observe after how many activations we will start to observe bit flips. The figure demonstrates that we will need 35K activations per aggressive row to cause some bit flips. Now we will switch to some other experiments and talk about what kind of observations we can make out of these experiments. And our goal was to learn the size of the sampler. For that, we perform a series of hammers and refreshes, and we perform this for 10 rounds. We will vary the number of aggressive rows and refreshes in the meantime. Okay, so let me explain to you the figure first. In the x-axis, we see the number of aggressive rows, and in the y-axis, we see the number of refreshes per round. And in each box, we have the number of bit flips per aggressive row count and per number of refreshes per round. If we check a specific row, we can see that as we increase the number of aggressive rows, the number of bit flips increase. And if we check a specific column, as we increase the number of refreshes per round, the number of bit flips decrease. You can see that these observations are consistent across all rows and columns. Now, if you just focus on the third column, where the number of aggressive rows is 2, we will see that adding a refresh reduces the number of bit flips from around 3K to 1, then adding the second one reduces this number to 0. Here we can deduce that the TRR mitigation acts on every refresh command. Before moving to the next observation, I just want to demonstrate how increasing the number of aggressive rows also increases the number of victim rows. As you can see from the left and right figures, we will have more neighboring, thus victim rows, when we have more aggressive rows. Now, if you look at the cases where the number of aggressive rows is 2 or 3, we know that the number of victim rows increases as well. The number of bit flips decreases significantly when introducing up to 2 refreshes, when the aggressive row count is 3, and it's decreasing significantly when we introduce 1 refresh when the aggressive row count is 2. We said after the refresh count is equal to the number of aggressive row count, the number of bit flips does not decrease significantly with adding additional refreshes. This is true as long as the number of aggressive rows is less than 4. These results lead to the following observations. The mitigation can sample more than 1 aggressive row per refresh interval, as adding additional refreshes reduces the bit flip count for multiple aggressive rows as well. And also, the mitigation can refresh only a single victim within a refresh operation, as each refresh reduces the bit flip count up to some point. This result is likely as a consequence of the tight timing constraints imposed by some DRAM timing parameters, which limits the number of additional refreshes that can be performed on a refresh command. But recall, the actual question is, what is the size of the sampler? We should look for a case where the number of bit flips stabilizes for refreshes less than aggressive row count. When this happens, we can conclude that we have overflowed the sampler, because even though we increase the aggressive row count and hence the victim row count, additional refreshes do not reduce the bit flips observed. As expected, we see the number of bit flips remaining constant for refresh count greater than or equal to 4 when the aggressive row count is 4 or more. This reveals the size of the sampler as 4. And this leads to the following observation. Sweeping the number of refresh operations and aggressive rows while hammering reveals the sampler size. The authors wanted to test this finding and see whether hammering more than 4 rows would cause any bit flips in DRAM modules with TRR protection. As you can see from the figure, hammering 5 rows circumvent the mitigation and create high number of bit flips. However, the random number of bit flips observed for increasing aggressive row count is not explained in the paper. We will now study another module, and the goal is to just verify the previous observations. And the prior experiments revealed the sampler size for this module as 6. Now, although we bypass the mitigation, we want to take this one step further and try to analyze the sampler to see if we can revive the more efficient double-sided RowHammer attack. The idea is to find the minimum set of dummy rows to overflow the sampler and trick the TRR mechanism. Then we select a specific victim row that we know to be susceptible to bit flips and for which we find in advance the threshold of hammers required to absorb bit flips, and we focus on that specific victim row. When the distribution of activations across aggressor rows and dummy rows and the number of dummy rows are varied, they absorb no bit flips at all. So the question to ask is, what might be going wrong? Further experiments suggested two other dependencies of the TRR mechanism. For example, the first one is DRAM command order dependency, which refers to the fact that sampler acts on specific DRAM commands. These are the first alpha activations after the refresh for A15 module. Another dependency is the address dependency, where the address of dummy rows affect the rows sampled by the sampler. And one possible explanation for that is the design of the sampler involves optimizations to reduce the storage cost of tracking row activations such that multiple aggressor rows addresses may conflict. We can conclude the following from these findings. First, the sampler records row activations as specific commands and likely at specific ordering of the commands, which is referred as command order-based sampling. And second, the sampling mechanism is affected by the addresses of aggressor rows, referred as row address-dependent sampling. So far, we have been talking about experiments conducted in a custom FPGA memory controller, but that is by no means representative, as now we have fine-grained control over the command sent in this case. What the authors tested next is the effectiveness of this new approach on a CPU. There are some challenges of such a test, though, since the sampling of the TRR mechanism is command order dependent and memory controller optimizes and reorders the request. This will make it harder to create access patterns that will trick the sampler. What is needed is to carry out a specific series of activations right after a refresh command to keep the inhibitor busy with another set of rows than the intended victim row, and this requires synchronization with the refresh command. And much fewer bit flips observed in this case compared to softMC, which suggests that we need a better solution for finding effective access patterns that trigger bit flips on TRR-protected DDR4 chips. The paper proposes TRRespass to effectively generate access patterns to bypass in-DRAM TRR mitigations. The design of TRRespass consists of cardinality, location, and fuzzing strategy. And next, we will talk about each of these components in a little bit more detail. So cardinality is a number of aggressor rows TRRespass is generating. It should be high enough to overflow the sampler, but the exact value varies across modules depending on the TRR mechanism employed. Increasing the cardinality too much is counterproductive, though, because a DRAM module cannot carry out more than a certain number of activations within the 64 millisecond refresh interval to the same row. So after some threshold number of aggressor rows, TRRespass cannot generate enough activations to create bit flips. And the second one is the location, and it's the relative addresses of the aggressors. It is randomized to maximize the probability of bypassing address-dependent TRR mitigations. For TRRespass, the access pattern is good if the number of unique bit flips it generates is high. TRRespass randomizes the cardinality and location parameters and evaluates the number of unique bit flips. It tests a chunk of memory to make the testing time practical. And for each chunk, it performs a test for 3 refresh periods to make sure that the victim rows are hammered for at least an entire 64 millisecond interval before they refresh. TRRespass is evaluated with Intel Core i7 device mounted on an Asus motherboard, 42 DDR4 DRAM modules from all 3 major DRAM manufacturers, currently representing around 95% of the market, are used during the evaluations. And to test TRRespass, the authors look for both 1 to 0 and 0 to 1 bit flips over 256 megabytes of physical memory. The analysis of TRRespass on all of these 42 DRAM modules then allowed the authors to generalize the assisted double-sided access pattern to a broader class of access patterns, which they call many-sided RowHammer. Here are the results of this evaluation. But I will not talk about this table in detail now, as we will cover it in detail in the evaluation sections. But if you just check the best pattern column, you can see the best pattern varies across modules. And here the key takeaway here is that there is not a single effective access pattern per module, which also verifies the claim that TRR is an umbrella term. Testing the effectiveness of TRR on mobile devices, we see that TRRespass can create bit flips in 5 out of 12 devices tested. This demonstrates that mobile platforms are also still vulnerable to RowHammer, despite the existence of in-DRAM TRR. And this is the complete set of results we have. And we now talk about the specific results we get from each vendor separately. This is the results we have for modules of vendor A. If you check the found patterns column from the table, you can see that for 7 out of 16 modules, TRRespass can recover effective access patterns. Also, if you check the total number of bit flips, we can see that on average, 16K bit flips are found by TRRespass across these 7 vulnerable modules we identified. Furthermore, the number of activations required to create bit flips is around 45K in these experiments, which is quite low compared to prior numbers reported in the original RowHammer paper from 2014. For vendor B, the number of bit flips observed is quite low compared to vendor A. This situation suggests that it is not easy to bypass TRR mitigation of these modules. The authors performed some additional experiments to see the possible causes of this observation. What they do is, they select specific aggressor rows that are known to be able to cause bit flips, and they repeat the same RowHammer experiment multiple times. The results show that the number of bit flips observed varies across iterations. The reason for this observation is not fully explained in the paper, though. And for the vendor C, TRRespass can induce bit flips for module C12 and C13. C13 is a newer module compared to C12, and the number of bit flips observed reduced drastically between these two modules, suggesting that in-DRAM TRR has improved over time. Another important result to see is the effectiveness of increasing refresh rate. Increasing refresh rate is a solution by itself, since doing so reduces the amount of time available for hammering. Also, since TRR acts mainly at refresh time, doubling the refresh operations could improve TRR security guarantees by enforcing the inhibitor to operate more frequently and refresh more victim rows. However, as the results show, TRR can trigger bit flips even when the refresh rate is doubled for several DRAM modules. So the key takeaway here is that this result further undermines the efficacy of double refresh as a stopgap solution against RowHammer, even when in-DRAM TRR is deployed. The final evaluation metric the authors used is the repeatability of the bit flips, which is an important factor for RowHammer exploitation. For one module per DRAM vendor, the best pattern found by TRRespass for this specific module is executed multiple times. And the experiment confirms that the bit flips are repeatable in a reliable way for all these modules. But it may require multiple attempts before obtaining the same bit flip again, and sometimes many other spurious bit flips might be generated by the same pattern. Exploitation with TRRespass resembles a normal attack with minor difference in repeatability. The exploitation starts with memory templating, where the memory is analyzed to find the right RowHammer access pattern. Then in the second phase, which is memory messaging, the target data is mapped to the available template found in the prior phase. Last step is to just exploit the pattern by triggering the same RowHammer bit flips on the target data. With these techniques, several types of exploitations performed by the authors, such as privilege escalation, access to co-hosted VM. And I think the key conclusion here is that we can mount real-world attacks on DDR4 devices with in-DRAM TRR protection. Let me summarize the work. The paper reverse engineers the TRR mechanisms employed in memory controllers and inside DRAM chips, which is PTRR and in-DRAM PTRR. This is the first work to show that DRAM modules with in-DRAM TRR are vulnerable to RowHammer. The authors also present TRRespass, which is a black box RowHammer test suite that generates effective access patterns to bypass in-DRAM TRR solutions. One key result of the paper is that it demonstrates you can create bit flips in 13 out of 42 DRAM modules. And This paper also proves that you can mount real-world attacks, and this paper also provides some hammering patterns for such attacks. But my key conclusion here would be that this paper improves our understanding of TRR significantly. So before I will continue with the critique, do you have any questions?
Yeah, so maybe I missed it, but I didn't see any results for modules with ACC. Is there any mention of testing such modules in the paper?
No, I don't remember such a thing.
Okay.
Yeah, but maybe I'm wrong. But I read the paper multiple times and I didn't see anything about ACC. Is there any other question? Okay, maybe I can continue with the strengths and weaknesses of the paper. So for me, the biggest strength of the paper is that it proves the effectiveness of in-DRAM TRR against RowHammer. It also develops many-sided RowHammer attacks that can bypass TRR mechanisms easily. The way TRRespass can induce bit flips is automatic, so there is no need to develop any algorithm for all modules. They also prove the exploitability of the attacks. I think it's also quite important that this paper is the first overview on in-DRAM TRR implementations where the authors uncover some of the underlying mechanisms and demonstrate that there are a variety of TRR implementations. The paper demonstrates that modern memory controllers do not employ TRR, which is important as it shows the importance of proving the security guarantees of in-DRAM TRR mitigations as we rely on them completely. About the weaknesses, I think the first weakness of the paper is that TRRespass is inefficient. It might not find a hammering pattern, or it might not find the best hammering pattern. For example, for the inefficiency, the paper finds the minimum hammering count as 25K, but revisiting RowHammer paper, which is a concurrent paper, finds chips with minimum hammering count as low as 4.8K per aggressive row. And maybe also due to this inefficiency, it can create bit flips only in 13 out of 42 modules tested. Also, you might not create an attack with these bit flips sometimes. The biggest limitation in terms of understanding is that the sampling mechanism is not fully understood or explained in the paper. For vendor C, TRRespass can only create bit flips in modules with MacValue untested, but the authors do not talk about this case and do not talk about why it might be the case. Is it just a coincidence or is there a specific reason? It's not clear in the paper. I found the quality of the writing poor. There are a lot of facts listed one after the other, and there's no cohesion between these facts. Also, some of the figure explanations were wrong, for example. And last step is I think it's subjective, but the vendor-based conclusions are not as insightful. So I can continue with the discussion points if still no one has a question. Okay, I'm just continuing. The first thing I would like to discuss is what kind of tests we can develop to figure out the underlying TRR mechanisms exactly. Because so far we have reverse engineered the sampler size and association of TRR refreshes with regular refreshes. But I think we still need to discover how to select victim rows to refresh and what is the sampling mechanism. So is there anyone who has an idea about this?
So I don't fully, again, maybe I missed this, but when the refresh, the PTR mechanism refreshes one victim row, or does it refresh a bunch of victim rows in the blast radius?
Okay, so the paper says it's also something I think is a weakness of the paper. The paper says as an observation that it doesn't say for the PTRR, but it says for the in-DRAM TRR that it just refreshes a single victim row. But I think like the correct thing is to say that it refreshes a limited number of victim rows. And for PTRR, like the memory controller implementation of TRR is not fully like investigated in the paper. So, but yeah.
And regarding your second question about the sampling mechanism, this recent paper called Graphene comes to mind. I guess Graphene came out, yeah, it came out after this paper. So, but do you have any idea of what implications that would have on this kind of sampling mechanism?
Yeah, no, I'm not familiar with the work, but yeah, if you have any thoughts, maybe you can share your thoughts.
Well, I'm in the same boat, so.
Okay. Yeah, okay, maybe I can continue with the next discussion point. So I think another issue is that TRRespass can bypass in DRAM TRR by increasing the cardinality, right? But would TRR be a viable solution if we increase the sampler size significantly? Because we know that there are no bit flips when the aggressive row count is less than the sampler size. So for example, I was reading this paper from 2020, which report minimum hammering count as low as 4.8K per aggressive rows. So I guess one key question here is that which of the following patterns is going to be more dominant when the minimum hammering count decreases substantially? Maximum number of activations per refresh interval divided by minimum hammering count, which is actually the number of aggressive rows we can create in a refresh interval, or the sampler size. Do you think which one is going to be more dominant? Like, can we increase the sampler size that much, for example? Okay. So I guess that no one has an idea about this discussion point as well.
I'm thinking about it.
Okay.
So, I mean, you posed the question. Can you maybe elaborate why? So you're saying tracking more aggressor rows would help, right?
Yes. So I mean, the way TRR is like bypassing these. The way TRRespass bypassing this TRR mechanism is that it creates many-sided RowHammer attacks, right? So you have many aggressive rows, and since your sampler size is limited, you overflow the sampler at some point. But like one basic solution is that just increase the sampler size, right? If you just increase the sampler size substantially, you can track all the aggressive rows, and TRRespass is not going to work. So for me, like there's a limit on the there's a limit on how much you can increase the sampler size, because like you have this, there's a cost associated with increasing the sampler size, right? But then also your minimum hammering count is decreasing, and as you decrease the minimum hammering count, you can create like potentially more aggressive rows in a refresh interval. And as you create more aggressive rows per refresh interval, you need to track more aggressive rows, which means like you need more like a bigger sampler size. So which one is going to be more dominant? So the question is, can we increase the sampler size like enough that we will capture all the aggressive rows regardless of the minimum hammering count we have?
But that's not enough, right? Like I agree. If you so you can bypass some of these patterns by tracking more aggressors, but you need to be also refreshing more victim rows at the same time. You need to do both, right? So with many-sided RowHammer, for example, if we have 20 aggressor rows and 19 victims, we probably need to be also on every refresh command be able to refresh all 19 victim rows, I would expect, to mitigate all the vulnerability from many-sided RowHammer.
Yeah, I agree. Actually, this is also related to the next discussion point I have. So even we assume that we increase the sample size enough, but like, do you think the sampler can always sample the RowHammer if it's not overflowed? And let's say even that, okay, so we just sampled all the aggressive rows. And like my next question is it just enough to capture all the aggressor rows? Because the same paper also says that for a given DRAM manufacturer, chips of newer DRAM technology nodes can exhibit RowHammer bit flips in more rows and farther away from the victim row. I think so the question here for me is that, so given the set of aggressor rows we have, how do we specify the set of victim rows? Because it's not just we increase aggressor row counts and like linearly the number of victim rows is increasing, because as you increase your scaling, you also get more victim rows per aggressor row, right? So I feel like this is not going to be a meaningful solution just to write aggressor rows and then sample all the victim rows, because there's not even linear relationship between the aggressor row count and victim row count. But maybe I thought someone has an idea that would make it feasible to just refresh all the victim rows, even when we have such like huge number of victim rows, or like someone has an idea on how to specify all of these victim rows given the set of aggressor rows.
Can you please describe how, so you mentioned that they're using some sort of fuzzing mechanism. Now, fuzzing is usually quite broad process. How does the fuzzer work? Because, of course, I agree that you can have farther away victim rows, but the fuzzer is also going to run forever, and I don't know. It sort of decreases the value of this data point that, okay, I have a fuzzer which might take forever, but the blast radius is also large. So I don't know. Would that work in all cases? I mean, that's why you have like 13 out of 42, right?
Yes.
But first of all, yeah, I would like to see like how do they decrease the search space of the fuzzer?
For TRRespass, you're asking that's right, the exact fuzzing strategy of TRRespass.
Not the exact, but just some basic idea of how the fuzzer is working.
Yeah, actually, you have only one paragraph for fuzzing strategy of TRRespass, which is basically why I like mentioned it only in 30 seconds. They don't explain it. They just say that, okay, they vary two parameters, which is the number of aggressor rows they have in the fuzzer and the location of these aggressor rows. And they say that they just have a black box fuzzing strategy. They vary these numbers, and in the end, like they just check for the number of unique bit flips. And like higher number of unique bit flips means a better fuzzing strategy for them. But this is all they describe. So I don't know the answer for that as well. But like, I think this is also a weakness, right? Because like later work also proved that all of these DDR4 devices with in-DRAM TRR protection are vulnerable to RowHammer. And they identified only 13 out of 42 DDR4 modules that are vulnerable to RowHammer. So yeah, I'm in the same page with you with this in this point, because they don't explain basically.
Okay.
Yeah, but does it matter? Like they vary, they say which two parameters they vary, and you know what? Like even if you choose them, pick them randomly, and or do search the entire parameter space. I guess at some point you will find every pair of parameters once, right? I cannot imagine exactly how you vary these two parameters would be extremely crucial here.
Yeah, I agree.
Yeah, but that some point might come in some exponential time which you have no idea, right? So you're just running. You're running it for days, and then someone comes and reboots your system and everything goes away.
Yeah, but for that, they say they only, like, to make the testing time practical, they say they only like test the specific small portion of physical memory. But again, they don't explain how do they vary the parameters. Do they look for like every combination of these parameters? Because I think you have 512 rows per subarray, and like you can increase the row, like aggressor row count, I think like to 20, 30. And if you get all the combinations of locations, for example, I guess you will have a lot of test case. Okay, so I'm just going to the next discussion. So like just having a different like approach, TRR in DRAM TRR relies on the execution of refresh command. But like, would it change the security guarantees of in DRAM TRR change if they were able to act independently of the refresh command? So my question is, once we have identified the target rows, do we have to rely on a refresh? I mean, we identified the aggressive rows. Can you think of any other mechanism to mitigate RowHammer other than refreshing the victim rows we have?
Wait, so if you don't, so my understanding was that refresh just allows you to constrain your time to 64 milliseconds or whatever. If you get rid of this sort of clock or sort of timing for implementation, then how do you decide, okay, now's the time to refresh? Basically, refresh is what is bottlenecking your RowHammer attack, right? So at some point you'll hit the 64 milliseconds, like you can have a limited number of hammers in 64 milliseconds. And so that's why you want to keep that window. But if you get rid of it, then you can't even determine when to do it.
Okay, so my point was that the TRR refreshes. TRR identifies a set of aggressive rows and then identifies a set of victim rows, right? And then when the TRR only refreshes the identified victim rows when there's a regular refresh command. And like this, because you have like you don't change the frequency of the regular refresh commands, it kind of limits the number of victim row refreshes you can have, right? For like as part of your inhibitor or like in TRR protection mechanism. So but I was saying that, okay, so TRR identifies these aggressive rows and then it then refreshes the victim rows. It just sends additional refreshes to these aggressive victim rows, sorry. But I was saying, so, okay, so we identified these aggressive rows, but why do we have to refresh the victim rows? Can we think of any other mechanism? So for example, what I was getting into here is that, so I was thinking maybe row clone can be an effective solution against RowHammer. I mean, if you remember from the earlier sessions, row clone is a fast mechanism to copy rows within DRAM. So I was thinking about something like that. Maybe we can remap the victim rows when the hammering count exceeds the threshold, or we can just remap the aggressive rows. So once we identify the aggressive rows, we don't have to really refresh the victim rows. We can just do some copies inside the DRAM. Because for example, if you just identify the victim rows, it is like basically a refresh operation for that victim, for example.
But why would that be faster? We need like one whole row clone probably takes more time than a refresh, right? And the problem isn't solved because we swap the data in these rows. Like with the new data being there, we still have the same problem, right?
For faster part, yeah, I guess refresh will be probably faster than just copying. But what I was thinking is that you're like bound by some like limit, even in terms of the number of refreshes you can, initial refreshes you can create. But you don't have any threshold for the number of copies you have within the DRAM row. What was the second point? Sorry, I forgot the second point you made.
That we still have the problem with the new data being there. I guess remapping would solve the problem of having like these two-sided RowHammers, right?
No,
so when we remap the aggressor rows so that they are not have one common row in between them, then the victim row won't be as attacked anymore, right? So that could be a point.
Wouldn't you spread out the attack more? I mean, even if you remap to here.
Sorry.
Yeah, so what I'm trying to say is that you have these two closed rows, and let's say that you've remapped far away.
Can they hear us if you speak like that?
I agree with what he's saying, right? The problem is still there. Even if you remap, the aggressor row still is getting constant activations, and maybe it will just move the problem somewhere else instead of solving it.
Yeah, because I was thinking about constantly remapping, so that like you will always remap the victims nearby. But yeah, I agree. I mean, it doesn't solve the problem because aggressor rows still can activate as much as they can. Sorry, actually I was, yeah.
What about, oh, sorry, yeah, go ahead, Philip.
You asked for a different solution than to refresh the victim rows. Well, that kind of turns into my paper that I'm presenting next. Instead of refreshing potential victim rows, we could just restrict the access to the aggressor rows and just throttle the amount of activations that a row can have per refresh window.
Yeah, I agree. This also can be a solution. Well, okay, so I was thinking about something like that, but in that case, for example, you kind of interfere with the other scheduling policies implemented in the memory controller, right? For example, if you just limit the number of activations to specific rows, maybe memory scheduler is doing something to just optimize the fairness within the scheduling policy, but then you just interfere with the policy. But if you just remap, for example, the complete, I think refresh is also in the same track. So if you just do something within the DRAM, and then you don't have to really interfere with anything in the memory controller part. But I agree, this is also a potential track.
Yeah, I guess that's a problem. So you can't really implement this in the DRAM itself. The thing with BlockHammer is to implement the whole system in the memory controller itself and have nothing, and no part of it is actually in the DRAM itself. So the whole system is confined into the memory controller.
Well, yeah, I agree with that. I think that would be kind of hard to do in the DRAM itself.
So as we were talking about remapping the aggressor and victims rows, maybe it could make sense to have, like, in each subarray some contain rows which are not affected by RowHammer, and then remap the rows which are being used for RowHammer to these contain rows which don't have RowHammer.
Yeah, actually, this is one prior approach on these tracks. I'm glad that you mentioned such an idea. I'm not sure if you are familiar with this paper, which is Crow from ISCA 2019. And the authors actually defined two other rows within each subarray. They call these rows as copy rows. And I think the main motivation for doing, like, separating these two rows is for latency reduction techniques. But then they realized that these two copy rows they have can be used to mitigate RowHammer. And then the authors proposed remapping the victim rows, not the hammer rows, to these victim rows, to these copy rows. But I think the idea is kind of limited, because I think it's a beautiful idea, but it's limited because, I mean, it can be changed, but they only consider remapping the victim row. But this can be changed, of course. And also the problem I think here is that the number of victim rows that can be remapped, or the aggressor row count, is limited, right, by the number of copy rows you have. So, for example, would you suggest something like that, like the variable number of copy rows you have in the DRAM, and then copy the aggressors to those variable number of copy rows, depending on the, like, attack you have?
I mean, we just need enough of these so that the normal refresh kicks in and refreshes all of the rows, so that no row is attacked anymore, right?
I'm not sure how many rows we would need though per subarray. Yeah, maybe we will, for example, if we will need 50 rows per 500 rows, then this will have a lot of storage costs, right?
Yeah, that's why I don't get why we would copy them instead of just remapping the aggressor rows to cells which aren't affected by RowHammer. Then we wouldn't need additional storage space. We could just swap the data we have there and swap the mapping as well.
Don't you, with this approach, effectively lower sort of you incur quite a large overhead, and since your threshold when you count something as an aggressor row is lower than the actual threshold you need to incur any kind of bit flips,
Mhm.
you start to copy aggressor and victim rows, whichever you choose, before anything actually happens.
Yes, like that's the idea. Otherwise, you'll get bit flips anyway. So I didn't get the question at all. Sorry. Oh,
So effectively, you're slowing down your system
okay.
before anything happens.
Yeah, I agree. But I guess that's kind of the case for all the RowHammer mitigation mechanisms, right? You have to somehow slow down the system as you interfere with the system. But do you think the overhead would be higher in this kind of approach?
Well, worst case, you have to copy back all of the rows that you have in these copy rows back to the original rows after every refresh, roughly, or whenever you choose to do it. If they're constantly being swapped out.
Yeah, I agree. So actually, I have discussed this idea with my mentors as them, and Giray sent me this Twitter link you can see in the bottom, where you can see the picture shared in this tweet. And I guess some similar approach is implemented. And the paper is going to be published in ASPLOS 2022, but the full PDF is not available. I guess at least I couldn't find it. But actually, we will see maybe some answers to our points in this paper and what they've done to mitigate RowHammer. So yeah, this was kind of nice for me to see this paper. But yeah. Yeah, maybe I can switch to next discussion point if you don't have any other comments for this one. So another point I would like to discuss is that so TRRespass considers only the cardinality and the location of aggressor rows while developing this hammering pattern. But as shown with this Micro 2021 paper, there are other parameters affecting the effectiveness of RowHammer. The first one is temperature. So they basically show it in the paper. DRAM cells are vulnerable to bit flips only in specific range of temperature. And the second parameter they mention is aggressor row active time. And I think it refers to the fact that there's a relationship between the amount of active time the aggressor row is open and the number of bit flips observed. I think in most cases, this relationship is linear. I think my first question about these observations is, can we develop attacks that are based on these other parameters? For example, the fuzzing strategy of TRRespass only uses the cardinality and the location, right? But can it also use a temperature or aggressor row active time? Or like in general, how do you think it would affect the mitigation mechanisms? Maybe I can explain my ideas a little bit more if you guys don't have any idea now. Is there anyone who has an idea now?
I mean, I suppose simply accessing the memory a lot would increase its temperature, provided that there's not enough cooling. So, well, you could, while fuzzing, also put additional load on the memory elsewhere. I don't know if you'd have to somehow distribute this across all banks to put load on all of them so that all of them become warm, or I don't.
Yeah, I'm not an expert as well. Yeah, but like in general, right? So, but also, for example, the most common mitigation mechanisms are based on refresh and also tracking aggressor rows, just to prevent the aggressor row from reaching the threshold hammer count, which is like, I think, the idea of BlockHammer in general. But like, for example, can we design mitigation mechanisms based on these other parameters? Let's say like BlockHammer also included the temperature to its fuzzing strategy. Then, for example, can we like integrate this temperature effect to TRR as well? Or like for example, we are talking about now temperature and aggressor row active time, but can you think of other parameters as well? That might affect the vulnerability of cells to RowHammer, or yeah, in general for such an attack. Okay, I'm just continuing with my last point then. So there are some circuit level solutions proposed, but we never talked about those kind of things in this presentation. And let's assume that we can solve this problem architecturally, and we are going to solve this problem architecturally. I have a very broad question now. Do you think it's better to have deterministic or probabilistic solutions? Because, for example, for the probabilistic solutions, we do not have full protection, right? Our protection mechanisms rely on some probabilistic mechanisms. But having said that, we also know that in DRAM TRR has some probabilistic mechanisms. Address dependency is one of them. And it made it difficult for TRRespass to bypass the in DRAM TRR mechanism for some modules. But also like deterministic approaches, they provide full protection. But like, do you think it will be easy to bypass these deterministic RowHammer mitigation mechanisms once we reverse engineer the exact implementation details of these mechanisms? Yeah, do you have any idea which one would you prefer? For example, a probabilistic mechanism or deterministic mechanism? What will be the overheads of such mechanisms in general?
Well, the goal would be to have a deterministic model that cannot easily be bypassed, even if you know the mechanism behind it. But the problem with deterministic approaches is usually that they are much more costly in terms of like area that you need to save information compared to probabilistic approaches like Para, for example, which is very easy. You just refresh nearby rows based on a certain probability that is very like area efficient. So the amount of area and energy requirements you have to put in to deterministic solutions might not be worth it.
Yeah, I don't really see a problem with the probabilistic solutions as long as the probability that something goes wrong is low enough, right? And what low enough means might be dependent on the context. Like for server applications, for security applications, it might be something different than for your usual home computer. And when you have enough protection that it becomes so that it isn't viable anymore to use that attack, it might be enough to have that kind of protection. So yeah. I wouldn't say that we need deterministic protection necessarily.
Yeah, at some point, I think there are just easier ways to defeat a computer than to rely on the small probability to defeat it with RowHammer. And as you said, I think it's a good idea to distinguish between certain applications. I mean, an airplane needs to be more reliable than your home computer. So maybe for things like this, or for, let's say, a bank, for which a RowHammer attack would be like detrimental, you would want a deterministic approach where you can actually prove that it works.
Yeah, I agree. Actually, that would be kind of a nice approach to really differentiate between the use cases and like design your mitigation mechanism based on that. But I think like my really last question would be, let's say we have a deterministic mechanism. Do you think like, can it really provide a full solution? I think the next presentation is going to be about BlockHammer, which I guess you are going to present it. Maybe we might get some answers to these questions as well. Like, can we have really full protection against RowHammer when we have a deterministic approach? So if no one has anything else to say, any other comments, I think that would conclude my talk. Thanks a lot for listening and like giving like your valuable opinions, sharing your valuable opinions. Yeah, I think I'm done if no one has any last-minute question or comments.
Given a probabilistic approach, if we can just correct the small number of bit flips that we still have with something like ECC, then we're basically in the clear, right? Since the problem with ECC is that it might not be able to catch all of the bit flips, if we can just limit the number of bit flips sufficiently or have them be so unlikely that it's basically guaranteed that we can catch them.
Yeah, okay, I have a question about that. What does small probability mean? Like, for example, I think this is how I approach. Like when you have a probabilistic mechanism, let's say you have some aggressor rows, and then you have some set of aggressor rows and some set of victim rows, depending on the set of aggressor rows you have, right? And then let's say you refreshed some of the victim rows you have, and then you decrease the probability of having a victim row that is not refreshed or protected somehow to very small probability. But it doesn't necessarily change the number of bit flips you have in this specific victim row, right? And I think the ECC is capable of only limiting like a couple of bits per cache line. And I cannot see how we can really decrease the number of bit flips we have in a victim row, because I think we either protect the victim row or not protect the victim row, but maybe my intuition is not correct. What do you think?
Yeah, sorry, I just wanted to get back to the application specific part once again. Like Philip named like lots of examples like banks and airplanes, but those don't really matter because there's no user provided software running on there, and you need that first to have to use RowHammer in any way. So when the software running on the airplane is written by the, I don't know, the company that built the airplane, then there's no way that they would accidentally trigger RowHammer. So it's really only a problem for server providers, I guess.
I mean, I was going to say that it would be silly to see this as a problem for something like a mainframe or something, or controlling system on an airplane. But it technically is possible that they do so many accesses to a single row that they do have bit flips. And if that does happen, then that's suddenly a big
I mean,
issue.
there's like a cache, right? you wouldn't like randomly do 20,000 accesses in a row without having some sort of cache in front of that.
But you also have non-cacheable data. And I think like for example, in one of the computer architecture lectures, the professor mentioned some of the applications that might, like real applications that might have such access patterns. But we also had, I think, yeah, I'm not sure if it was in the seminar section or seminar session or computer architecture session, like there has been such a discussion before, and I guess Giray, it was maybe during Giray's presentation in computer architecture course, and he mentioned that he has never came across such a attack pattern in a real application. But yeah, but maybe because like especially with the scaling, right? You have the number of hammerings you need is decreasing, so maybe you will have well, yeah, I don't know as well for sure.
Yeah, thanks a lot. I just want to come back to that. Like for server providers, we would still have that problem. But I guess if we have a probabilistic solution which has some low enough probability, at some point software could kick in and like evict that software from the server. I don't know. Maybe hardware only has to provide protection up to some point, and then software can take over.
Yeah, I mean, you mean like hardware also reports the thread that is like doing hammering, like RowHammer.
Yeah. Maybe it reports every 10th problem to the OS, and then when these happen too often, we can say that this can be on by accident.
Well, to that regard, BlockHammer has a technique that actually does a very similar thing called attack throttler. This mechanism identifies threads that are likely to be RowHammer attacks, and it exposes this information to the operating system. So the operating system can see which threads are likely to be RowHammer attacks and can basically just kill the thread.
Yeah, interesting.
Yeah, I guess I have no comments about the, like your discussion. So is there anyone else who wants to share any other comment again, or? Okay, I guess we are done this time for sure. Thanks a lot for sharing your opinions. I enjoyed it. I guess, yeah, that's all from me. I can stop sharing.
Okay, great. Yeah, thanks for the presentation, Banu. And it was a very good discussion actually on an important topic. And I don't think there are answers to this topic. So this is a very open research area at the moment. All the questions raised, as far as I know, don't have answers. For example, how do you change the fuzzer to take into account these new properties of RowHammer: temperature dependence, active row regressive time dependence, and depends on spatial location of the vulnerability. I think that's something that someone can do for sure, and definitely solving the problem in a low overhead way is still an open problem. And I think you guys have actually talked about interesting ideas, combining multiple solutions, software and hardware. I think those are actually good directions, and combining, trying to reduce the probability of bit failure such that ECC can deal with it. I think that's certainly important also. The question is, how do you do all of that at low overhead? So this is definitely a good area of research. And let me comment on the historical importance of this paper. By the way, I will mention the fuzzing issue. I think you guys spent some time on fuzzing, which is a topic that I don't consider really that important, because people in security have worked on fuzzing for decades. And they basically do a lot of different types of fuzzers, randomized, non-randomized, etc. And the source code of this paper, TRRespass fuzzer, is available. So that's one of the reasons why we didn't really want to spend much time describing the fuzzer. In the end, it has a strategy. Yes, it's limited. And as a result, the results of the paper are also limited. But the value of the paper really comes from the fact that it proves indisputably that you can bypass these TRR mechanisms. Now, there was a lot of talk before this paper saying that, oh, DRAM manufacturers solve the problem, so why do we care about RowHammer? So we shouldn't do research, etc. And this paper proved indisputably that DRAM manufacturers did not solve the problem, basically. And if you read DRAM manufacturers' press releases before this paper, they basically said that RowHammer is a solved problem. It's very aggressive, actually. At least two of them did this. And of course, a lot of people in the community did not believe that it was solved, but this is the evidence that it was solved. This, along with the paper that Jeremy wrote for ISCA 2020 that Banu mentioned, these are the two papers that show that RowHammer has to be taken much more seriously. And that led to a working group at JEDEC to be formed by the industry, mainly pushed by some big vendors like Microsoft, Google, etc. And that working group still works. It's not very transparent, unfortunately. That's the way JEDEC, the industry committee, works, and they try to find a solution. I'm not really sure. They published actually several white papers that you can find online if you're interested. But yeah, I'm not. I think the solution needs to be much better, basically. And there are a lot of interesting ideas, like remapping idea is interesting, but yeah, it clearly has overheads. And you mentioned the Crow paper. Yes, that's the first paper that discusses the idea of remapping rows internally with internal DRAM support. And I think certainly there's something there, but it needs to be done carefully because it has overheads, right? I think somebody pushed back saying that, oh, why not refresh if you're going to remap? Yeah, I mean, certainly I think it's good to understand the relative overheads of these mechanisms. Yeah, I guess I don't have much to add at this point. It was good discussion, but at this point, I think it's clear that we do not want solutions that we cannot verify easily or we cannot prove well, okay, there was this last discussion that you mentioned on whether, let's say, benign sort of applications can cause this problem. I mean, and the right answer is we don't know, but there's certainly anecdotal evidence in industry that this problem has been seen in some applications, in very rare cases, where the application doesn't do a lot of caching, etc., and then it gets these bit flips due to RowHammer. So there's anecdotal evidence. Of course, replicating this application is a difficult thing because it's anecdotal in the end. But as the RowHammer threshold reduces, there's no reason why some benign applications can get into that territory, right? And maybe it may not be easy, but there's a lot of software out there, and who knows, right? So I don't think you want to, let's say, you want to bet the safety of your life on caches being exploited by applications, and even by benign applications, right? Because that flip may kill you literally. That's my perspective on these things. So if you've been talking about safety critical applications, the question is, okay, it's safety critical. How serious are you about your safety at that point? Do you want to trust and say, okay, my cache hierarchy will take care of it, and I'm fine flying this plane that's vulnerable to RowHammer with scale technologies? Or do you want to not trust that and say, let's solve the problem so that we can trust our machines? I think I'm in the second camp. I think my life is a lot more valuable than a cache is protecting it. Okay, I'm done.
So thank you very much, Bana. Honor everybody involved in the discussion. It was really nice. So we will continue with the second talk, BlockHammer. So is that okay if we live stream this on YouTube, or should we just like, should we stop live streaming? What do you think, Philip?
Yeah, you can just keep live streaming this.
Okay. So yeah, this paper is also a new paper from earlier this year. It's called BlockHammer, about mitigating or defending systems against RowHammer attacks. So Philip will present this paper, and yeah, so Philip is a third-year undergrad, and he did a good job, I think, preparing this slide deck and getting ready for his talk. Yeah, we're back to you, Philip.
Okay, thank you for the introduction, and welcome everyone to my presentation about BlockHammer, preventing RowHammer at low cost by blacklisting rapidly accessed DRAM rows. I will start with the executive summary of the presentation. The paper presents a mitigation technique for RowHammer. This is a hardware vulnerability caused by accessing the same memory rows with a high frequency. This can lead to bit flips in adjacent memory rows. The paper defines its main goals to efficiently and scalably prevent RowHammer attacks without knowledge or modification to DRAM internals. The key idea is to keep track of row activations to blacklist rows that are being accessed too rapidly. The mechanism provided is called BlockHammer, and it mitigates the RowHammer attack in two components. First, row blocker blacklists memory rows that are being accessed too rapidly. And once a row is blacklisted, its accesses are restricted to a safe frequency. And secondly, attack throttler identifies potentially dangerous threats and limits their memory bandwidth. This increases the performance of benign threats while the attack is occurring. The paper evaluated the performance of BlockHammer compared to other RowHammer defenses, and it found that while the system is not under attack, the performance is competitive to the alternatives. Furthermore, while a BlockHammer attack is occurring, the performance increases significantly compared to other mitigation techniques. So this is the outline of my presentation, and we will jump right into the problem. DRAM organizes its memory cells as a two-dimensional array, and accesses can be performed one row at a time. When activating a row, its content is being transferred to the row buffer. The individual cells are not perfect, and they will lose their state over time. At some point, the bit cannot be read reliably anymore, and this means that the cells need to be refreshed periodically. The RowHammer vulnerability is caused by repeatedly activating the same row of memory. Hammering a row in this manner will effectively increase the speed at which nearby cells lose their state. At some point, the refresh mechanism cannot keep up anymore, and a bit flip might occur. One can now ask how serious this exploit can be, because targeting a specific cell would be challenging. It has been shown, however, that RowHammer can be used to gain kernel privileges on certain systems. One can also ask if more modern DRAM chips are more resilient to RowHammer. However, previous work has shown that the exact opposite is the case. Chips are getting more and more vulnerable to RowHammer. This phenomenon has two main causes. First, the individual cells are getting smaller and have less charge, so there's less effort required to make them flip. And as the memory becomes denser, the physical distance between the cells shrink, so further increasing the effect hammered rows have on their neighbors. Since RowHammer is a major concern, there have been many proposed solutions in the past. The paper acknowledges four main ways to mitigate this problem. First, and maybe the first and maybe most obvious solution is to simply increase the refresh rate. If increased far enough, an attacker cannot hammer enough times to make a cell unreadable before it gets refreshed. The obvious problem with this solution is that while not under attack, the memory is getting refreshed unnecessarily. This wastes both time and energy. A second and more clever approach is to reactively refresh neighbors of recently activated rows. Though better than the first solution, even this approach comes with a decrease in performance. The third proposal is to physically isolate memory regions owned by different threads by putting buffer rows in between. This approach obviously wastes space in memory. The last method is to proactively restrict the accesses to the same memory row to a safe frequency. This will also throttle the accesses made by harmless applications, however. The paper formulates two key challenges a mitigation technique has to overcome in order to be successful. Since the DRAM vulnerability is getting more and more serious, the methods need to be able to scale in order to keep up. Simply increasing the refresh rate even further will waste even more and more time and energy of the system, and is obviously not scalable. Reactively refreshing also needs to be more aggressive. leading to more and more unnecessary refresh when not under attack. The physical isolation will require more buffer rows between memory regions, which in turn will waste even more space in memory. And the proactive throttling will need an even lower threshold and will affect even more benign applications. The second challenge is to make the method compatible with commodity DRAM chips. Two memory rows that have physical addresses next to each other are not necessarily physically adjacent in the DRAM implementation. The memory layout is proprietary information to DRAM manufacturers and is therefore not easily available. Increasing the refresh rate does not require any knowledge of the memory layout. In order to reactively refresh potential target rows, however, the system needs to know which memory rows are physically next to each other. This knowledge is also required to put buffer rows in between different memory regions. And lastly, throttling the accesses to same memory rows also works without knowing the memory layout. This brings us to the four main goals this paper poses to its own mitigation technique. It needs to address a comprehensive threat model without making any major assumptions about the attacker. The technique needs to be compatible with commodity DRAM chips without knowledge or alterations to their internals. It also needs to be scalable with increasing vulnerability to RowHammer attacks. And it wants to be deterministically preventing all RowHammer attacks. It even goes so far as proving that there cannot be any successful attacks on the system. We will now start talking about the main focus of the paper, BlockHammer itself. BlockHammer uses two components to mitigate an attack: RowBlocker and attack throttler. RowBlocker makes use of area-efficient Bloom filters in order to keep track of row activation rates. It uses this information to blacklist potentially dangerous rows and restrict their accesses to RowHammer safe frequencies. This component is enough to guarantee RowHammer safe operation. The job of attack throttler is to identify threats that are likely to be RowHammer attacks. And attack throttler then reduces the memory bandwidth to those identified threats. This greatly improves the performance of benign threats while the system is under attack. We will first take a look at RowBlocker, and this is a high-level schematic and we will come back to it once we understand its components. The first component in red is the blacklist. It is used to keep track of the row activation rates. The second component in green is the history buffer, and it's used to keep track of the most recent row activations. We will start talking about the blacklisting mechanism. RowBlocker BL keeps track of the number of row activations for each row. A very naive way to implement such a system would be to associate each row with a counter, just counting how often a given row has been activated. This approach is prohibitively expensive in terms of area requirement, however. The paper realizes that false positives are tolerable as long as they are infrequent enough. In other words, occasionally blacklisting a harmless row is okay. False negatives, however, are bad. Not blacklisting a dangerous row might lead to bit flips. This realization makes it possible to weigh up false positive rates to area requirements. RowBlocker BL uses area-efficient unified counting Bloom filters for blacklisting, and I will explain how they work in 3 steps. I will first talk about Bloom filters. Then we can generalize them to counting Bloom filters. And lastly, I will introduce unified counting Bloom filters. So let's talk about regular Bloom filters. They consist of an array of bits and a set of hash functions. And there are 3 methods implemented on this data structure. Clear, the insertion of an element, and the test for an element. Clearing a Bloom filter is easy. We just set the whole array to zeros. Inserting an element X into the Bloom filter is a bit more interesting. We evaluate all the hash functions for X and set the corresponding bits in the array to 1. Inserting a second element works in the same way. If the element was already set to 1 by a previous insertion, the bit stays 1. In order to test if an element is in the data structure or not, the hash functions are evaluated as well. If 1 or more of the corresponding bits is 0, we can be certain that the element has not been inserted into the data structure. This simple data structure only allows us to see if a row has been activated or not. We are interested in the number of times it has been activated. That's where counting Bloom filters come in. By replacing the area of bits with an array of counters, we can alter the data structure as follows. Clearing stays the same, just resetting all counters to zeros. And inserting the first element is also uneventful. But inserting the second element will increase all corresponding counters and will produce a 2 in this case. If we insert an element for a second time, it will increase all corresponding counters again. If we want to test how often an element has been inserted into the filter, we evaluate all hash functions and look at the counter with the smallest value. This gives us an upper bound on how often a given row has been inserted into the filter. A row gets blacklisted once a given threshold is reached. So let's talk about unified counting Bloom filters. Bloom filters have one critical flaw. They saturate over time. Since we only increase the counters, all the counters will eventually tend to infinity. And this will increase the rate of false positives. This means we have to clear the filters periodically, but clearing a filter will lead to all information to be lost at once. This will lead to potentially dangerous rows not being blacklisted anymore. Unified counting Bloom filters solves this problem by combining 2 counting Bloom filters in the following way. The elements are always inserted into both Bloom filters at the same time. And only one filter is cleared at a time. And they take turns in doing so. The test queries are always answered by the least recently cleared filter. This gives each filter time to warm up before becoming active. Let's see how 2 counting Bloom filters here called CBFA and CBFB work together. The green bar shows that the corresponding filter is active in a given epoch. The other filter is passive. Let's assume that a row is activated rapidly at the beginning, and it stops being activated after 2 epochs. At the beginning, the row is not blacklisted since the threshold has not yet been reached. At some point, the activation count reaches the threshold, and the row gets blacklisted. The row then remains blacklisted for the remainder of epoch 1. At the beginning of epoch 2, CBFA gets cleared, and CBFB becomes the active filter for the next time window. Since CBFB knows the high activation rate during the first epoch, it keeps the row blacklisted for the entirety of its epoch. At timestamp 4, the row exceeds the threshold for CBFA again. And at the end of epoch 2, CBFB gets cleared and CBFA becomes active again. Since the row is not being activated anymore, the counter stays below the threshold and will no longer be blacklisted at the beginning of epoch 2. Let's now talk about the second component of row blocker. For a bit flip to occur, a row has to be activated with a minimum frequency. So if we keep a certain amount of time t delay between each activation, we can guarantee RowHammer safe operation. In order to achieve this, the RowHammer HB maintains a first in, first out history buffer containing all row activations in the last time window t delay. For a row access to be delayed, 2 conditions need to be satisfied. For a row access to be delayed, 2 conditions need to be satisfied. The row needs to be blacklisted by row blocker BL, and the row needs to be in the history buffer, meaning it was activated in the last time window t delay. By combining those 2 concepts, a row can be accessed as rapidly as possible until the blacklisting threshold is reached. At this point, further accesses are getting spaced apart by t delay. Let's take another look at the high-level schematic. Before a memory access is performed, a query is sent to RowBlocker asking if the access is RowHammer safe. RowBlocker checks the blacklist and the history buffer at the same time. And only if it is both blacklisted and recently activated will the row activation be delayed. Every time a row activation is performed, both the blacklist and the history buffer will be updated. We will now start talking about the second main component to BlockHammer. Row blocker alone is enough to ensure that no bit flips occur. The job of attack throttler is to identify threats who look like RowHammer attacks and to throttle their memory bandwidth. This will prevent a RowHammer attack from using up most of the available memory bandwidth. In order to identify potentially dangerous threats, the attack throttler uses a RowHammer likelihood index between 0 and 1. This index is proportional to the amount of blacklisted row activations. So a harmless threat will have a RowHammer likelihood index of near 0, because no blacklisted rows are being accessed. And a thread performing a RowHammer attack will have a RowHammer likelihood index near 1 because it will repeatedly try to access blacklisted rows. As the RowHammer likelihood index goes to 1, the memory bandwidth will be restricted more and more. Optionally, the operating system has access to this index as well and can take further actions as it sees fit. We will now take a look at the evaluation of BlockHammer provided in the paper. The paper compared BlockHammer to 6 state-of-the-art RowHammer mitigation techniques called Para, ProHit, Murloc, CBT, Twice, and Graphene. We will start by comparing area and power requirements for a RowHammer threshold of 30 to 1,000, which is a reasonable assumption for current technology. We can see that RowHammer's requirements are similar to those of CBT, Twice, and Graphene, but they lag behind ProHit and MRLock. This is because ProHit and MRLock are non-deterministic approaches, which can be much more area efficient. We can now take a look at how the requirements change for a more vulnerable machine. The paper sets the threshold from 30 to 1,000 down to 1,000 and observes that the requirements for BlockHammer scale more efficiently than other mitigation techniques. One thing I was worried about while reading the paper was if the blacklist lookup would increase the memory latency. The paper shows that the lookup takes about 1 nanosecond. A DRAM row access takes on the order of 50 nanoseconds. This means we can check the blacklist while the previous request is being processed. This ensures that no extra latency is required. For the performance evaluation, the paper distinguishes between 2 cases. Either an attack is occurring or not. Let's take a look at the case without an attack first. The paper uses 4 metrics: system throughput, job turnaround time, unfairness, and DRAM energy consumption. As we can see, the red bar corresponding to BlockHammer is very close to the baseline. Overall, BlockHammer introduces less than 0.5% performance and 0.4% DRAM energy overheads. We can also take a look at how the performance changes with increasing vulnerability. But as we can see, the performance overheads remain negligible, looking at the red line. Let's take a look at the performance when a RowHammer attack is present. As we can see, both performance and energy requirements improve compared to other techniques. Thanks to Attack Throttler, we observed a performance increase of 45% and a decrease in energy consumption by 29%. The paper also compares how the performance benefits scale with increasing vulnerability and found a performance increase of up to 71% compared to the baseline. Before we will now jump into the strengths and weaknesses, if anyone has questions about the mitigation technique, about BlockHammer, about anything I just presented, you could ask them now, or I guess you can ask them later as well. So we will now discuss the strengths and weaknesses of the paper. First and foremost, BlockHammer seems to be a simple and efficient mitigation technique, and it only evolves the memory controller without any knowledge or alterations to the DRAM internals. It also scales better with increasing RowHammer vulnerability than other mitigation techniques. And so it is likely that the benefits over other techniques will increase over time. Attack Throttler is a neat idea that reduces the performance impact on RowHammer attacks on a safe system. The paper also clearly motivates why another RowHammer mitigation mechanism is needed, and it clearly states its design goals for BlockHammer. BlockHammer works in a deterministic manner, and the paper even goes as far as proving that no RowHammer attack can defeat BlockHammer. Now let's get into the weaknesses of the paper. Some of the benefits of BlockHammer only get apparent once the superior scalability has kicked in, especially compared to the non-deterministic approaches like MRlog and ProHit. The area and energy requirements are quite a lot higher. One could also try to abuse the Bloom filters by saturating them. Let's say we hammer many different rows at a rate which is barely below the threshold. We could saturate most of the counters and increasing the false positives rates of other applications. This would obviously lead to a loss of performance. The paper mentions 6 mitigation techniques by name and uses them to evaluate BlockHammer in chapter 6, but then introduces the mechanisms in chapter 7, which didn't really make sense to me because I was Googling them in chapter 6. The graphs feel a bit cluttered, especially the one with comparing the scalability of the different techniques. They're a bit small. Most of the data points are not even visible because they're behind other data points. So let's get into the discussion. The reason why we need unified counting Bloom filters is because we need to desaturate the Bloom filters at some point without losing all information at once. But another way to desaturate a Bloom filter would be to simply divide all the counters by 2. So are there any ideas how we could desaturate a Bloom filter without losing all its information at once? Or are there any comments why maybe dividing all the counters by 2 is not a good idea?
Yeah, I'm not sure if division is the correct operator because it doesn't model how we see the past. I'm not sure if that makes sense now. It doesn't correlate to anything in the real world. So instead of dividing, we could instead like subtract everywhere constant, which indicates like the maximum number of accesses one could make in the period of time to the point where we last subtracted something. So every like a few milliseconds, we subtract a certain constant. And then the Bloom filter would always contain the data of the last time period.
That might actually be a solution as well. The thing with dividing is it is very easy to implement. You just bit shift. But yes,
Yeah, that's true. Yeah.
You could also subtract. You would probably have to be very very precise on how much you subtract and how often you subtract in order to not allow someone to hammer a row just below this threshold where it gets so it gets subtracted enough so it doesn't actually blacklist the row.
With division, we lose information really quickly, like exponentially.
Yeah, of course that's true as well.
Yeah, I guess we would need some kind of experiment to figure out what's better. But what would be the main benefit of just having one Bloom filter? Mainly area cost?
Mainly area cost. I mean, the Bloom filters are one of the main contributors to the area cost of the whole system. So if we can provide a solution that only requires one of the Bloom filters, we basically cut the area cost in half, which would be significant.
Do you know like a percentage of how much is like taken over by the Bloom filter and how much by the
yeah,
buffer?
we can take a look at that if I can find the slide. Oh, it's not actually on the slide. It's only in the paper.
I have a related question. So, yeah. So, wouldn't performing operations directly on the values inside Bloom filters create problem because it comes from a hash function? So essentially, it's a transform value. It doesn't seem like a good idea to make some change on that value without performing the transformation in reverse.
We're not doing anything with the values we are putting in there. We just lower the counter. So we're modifying the counter, and the counter which normally gets incremented on each axis. So that's all operating on the output of the hash function. Okay.
So back to your question for a second. The whole implementation takes about 0.14 millimeters squared, and the dual counting Bloom filters take 0.11, which means that's like 60–70% of the whole area cost is required by the Bloom filters. So cutting that area cost in half would basically translate to a in area decrease of 1/3 in the entire system. And
but at the same time, you're like shifting circuit would take some memory as well, because you can shift in place, I guess, in a single clock cycle. So you would need to duplicate each of these memory cells or do it like line by line. I'm not certain if division or like subtraction would actually lower the area cost.
I would think that you would be able to just shift in place, but I might be wrong about that. So
yeah, I mean, you would override the data that's already stored there. If you
you have to start at the end where you shift the bit like outside and just throw it away.
Right. But then you would do it like one after the other, and then it would mean an additional latency cost, I guess.
Yeah, but you have time. You have enough time to do that because, as we discussed, the each lookup only takes about 1 nanosecond, and a DRAM activation takes about 50. So we have 49 nanoseconds of extra time where we don't really know what to do with.
Yeah, okay, then that could actually make sense. Do they have any comment on whether clearing and having 2 filters is the only option? Like the authors of the paper.
In the actual paper, there's no discussions of this option. This is the thing I came up with while reading the paper, so
Yeah, okay.
I thought it would make a good discussion point at the end.
So I don't see any immediate downsides, but I'm not an expert on this.
Yeah.
So yeah, it would certainly change the characteristic, because now you have like a exponential fall off where you have in the previous time step half the weight, and then the time step before that a fourth, and so on. So I think probably it was also then you have to change around how much your threshold is for like blacklisting certain memories, because now let's say you counted 10 activations in one time step, and now you're beginning at the next time step, and now you're halving it, and now you have 5, and then if previously 10 was your threshold, then you would have blacklisted it for the entire next frame, but now suddenly you only have 5 at the beginning, so it could potentially be missing things. So
okay, yeah, that makes sense. This
yeah, I see the point, but subtraction would actually make the arithmetic work the same.
yeah, subtraction would be a bit nicer, I guess.
Much more expensive if we subtract by constant. I mean, we don't want to subtract like 2 numbers given as wires, as inputs.
Well, there's one more problem that I didn't really tell you about, because I think I just forgot to mention it. When a Bloom filter resets, the hash functions get randomized. So the if a certain row has like false positives because of some reason, in the next cycle, the false positives will most likely not be there anymore because there are other hash functions being used.
Okay, yeah, that mitigates the tag vector you mentioned in your weaknesses part, right?
Yes, there's this is one of the mitigation techniques that this is one of the things that would mitigate this, but I don't think you could entirely get rid of it. If you just hammer enough.
If your software doesn't know about how the hash functions are recomputed, it can predict where like the collisions would happen. So there's no way of doing it deterministically and repeatedly.
Yeah, but first of all, relying on not being able to determine the hash functions might be a bit
like if they get randomized, you don't know the random values that they are getting fed.
Kind of depends on the way you actually randomize them with.
Yeah, it does, obviously. Yeah, but I guess that kind of makes the solutions with dividing by 2 and subtracting obsolete. They're not obsolete, but shows why they don't work. They don't.
Well, they would get rid of this mechanism. The other mechanism,
like we can't use like subtraction and division and have the counter being like the hash functions being randomized, right?
Yes, this would be a problem.
And then we would have that detect vector again, and the rate of false positives would be higher.
Yes.
For it, so shouldn't have necessarily get rid of it. So what you could do is you could like save the previous hash values and the current hash values, and then or hash settings, and then if you want to look up, you could like combine those two and make a lookup for okay, what have been the previous value and what would have been the current value, and then take like a maximum or a sum of both. But then you could have more false positive. But yeah, that would, so it
That's
wouldn't
an
rule it
interesting
completely
solution.
out, but yeah. But I think yeah, it would probably be better to have just two.
It's kind of funny how those discussions actually go in very weird directions. I never thought about that, but yeah, I guess you could do that. I mean, I don't see why you wouldn't be able to do that. Does anyone else have anything to say about the resetting of or the desaturating of the Bloom filters? I guess if not, either you can just bring them up as they come, or we just talk about the next thing. The main thing that makes row blockers so much better in the case that a RowHammer attack is present is the ability of attack throttler just throttling the memory bandwidth given to an attacking thread. But would there be a solution to retrofit the attack throttler to other existing RowHammer mitigation techniques? The thing we would need is attack throttler relies on the RowHammer likelihood index, which is currently computed by the blacklisted row activations, which would not be a thing in other RowHammer mitigation techniques. So we would need another way to determine which threats are likely to be RowHammer attacks.
I mean, for any kind of a mitigation where we keep track of which rows we suspect to be RowHammer attacker rows, we could count accesses to those and then
yes,
do the same thing, right? So given we have that, it should be possible. That might not be all of the mitigations, but
yes, but some of the other mitigation techniques also keep track of row activations in other manners than RowBlocker does. They don't do it with Bloom filters, but when you have this information, you might as well use it in order to identify threats that are potentially dangerous.
right, I have a question about attack throttler. How does it decide that a thread is actually attacking? Does it use a fraction of accesses or just a threshold, another one? I think I missed that.
1 second. So attack throttler uses a RowHammer likelihood index. This index is capped between 0 and 1. And if you have only memory requests to blacklisted rows, the RowHammer likelihood index becomes 1. So the attack throttler is basically sure that you are trying to perform a RowHammer attack. And if you never access any blacklisted rows, then your RowHammer likelihood index is 0. And attack throttler is basically sure that you are not trying to attack the system, at least not with a RowHammer attack.
So if I keep my accesses to blacklisted rows low enough, I can sort of deceive the system into thinking that I'm not attacking it, or does that?
Well, but if you want to attack the system, you want to hammer a single row over and over and over again. And at some point it becomes blacklisted. And if you keep hammering it, you will then access blacklisted rows, which will increase your RowHammer likelihood index.
Right, can I? The thing is, how do you compute the likelihood index? Because if I can schedule, if it's just a fraction between blacklisted row activations and non-blacklisted row activations, can I make enough non-blacklisted activations so that I can offset the blacklisted activations that I'm making to hammer a row?
Yes, you could do that. So you could theoretically get around the attack throttler, I guess. But this will not allow you to get a RowHammer attack working, because the row blocker itself is enough to mitigate an attack, but you could get around the attack throttler in that way. So your memory bandwidth does not get decreased.
Right, because as soon as a row is blacklisted, it's basically safe. Yeah, okay, thank you.
Yes. That was not the slide I wanted to. Okay.
So I think this is a good discussion, but I guess I need to make a correction. So it is not the ratio of blacklisted row activations over not blacklisted row activations. It is the ratio of blacklisted row activations in a fixed time window. Or like so in the denominator, you actually have the total number of row activations you can perform, total number of blacklisted row activations you're allowed to perform in a fixed time window. So without reaching 1, actually you cannot, like an RHLI value of 1, you cannot actually reach to RowHammer threshold to induce a bit flip. So if you reach the RowHammer threshold, induce a bit flip, that means that it's guaranteed your RHLI is going to be 1 or larger. And when it is 1 and you have attack throttler in the system, then you do not allow any further requests from this thread. So it will not exceed 1. If you have BlockHammer and attack throttler, everything is configured correctly. So I think there is no danger of, or at least like this is not, this kind of access pattern is not really the way to have a workaround of attack throttler.
Yeah, I guess I misremembered that, to be honest. Yeah. And the next question we could have is, instead of using the unified countering Bloom filters, are there any other data structures that are worth considering for a blacklisting mechanism? Okay, I guess people are getting tired. So let's get to the last discussion point, which is a pretty open one. Is it actually better to solve the RowHammer problem in the memory controller itself, or is it better to do it in the DRAM itself?
Yeah, sorry, but now I'm curious what your answer to the third discussion point would be, because I thought about the question but couldn't think of any other data structure which would make sense to implement in hardware for implementing such a mechanism.
Well, graphene takes a kind of similar approach to this problem, but it uses a completely other data structure. It uses a let's say if I can actually find it, to a frequent element detection algorithm, and maybe you could use that in order.
I have no idea what that is, but sure.
Yes,
it's not a Bloom filter of any kind.
No, it is not a Bloom filter. It will keep track of the most frequently used item of a set.
Deterministically, without any hash function or something like that.
Yes, it does produce false, or it does overestimate, I think.
Yeah, okay, so it sounds interesting, but I wouldn't know any data structure which does it, like, would be better suited.
Yes, but I thought I might as well ask it, because in a room with I guess by now 18 other people, there might be someone who can come up with or who has heard of something that might be a good solution to this problem as well, except for Bloom filters, which we already discussed.
Sir, I think I heard a data structure called min sketches. I think they kind of resembles Bloom filters a lot, but I don't know the difference between actually Bloom filters and sketches. Have you heard of sketches as well?
I did not quite understand you there, but
Oh, okay.
Say again.
So there are, I think, data structures called sketches. They also resemble Bloom filters a lot. They also operate on hash values, but I guess there are some differences in the way they provide some probabilistic guarantees. But actually, I don't know. Like, for example, there's this something called min sketch, but I don't know the difference between min sketch and counting Bloom filters. Maybe if someone sort of sketches as well, there could be maybe also something.
Okay. Yes, to be honest, I have not heard of that, but it sounds like a idea that I might actually want to look into, or a mechanism that I might want to look into.
Well, yeah, potentially. Yeah, actually, I don't know the difference, and I'm curious if anyone knows, because I was wondering what's the difference between these Bloom filters and sketches. That they resemble each other a lot, but maybe one of them will be more scalable compared to the other one going forward.
Yeah, I mean, there has to be a reason why this paper used Bloom filters. So, but taking a look at sketches can't hurt, I guess.
Yeah, so for the last question, I'm not sure if it's better to pick one as memory controller or DRAM. I mean, do you have any opinion on why we should pick one and rather not go for both?
Because most of the time, those things are not done by the same manufacturer. So you have a memory controller that has nothing to do with the DRAM chips you put into your system. So actually, communicating between those mitigation techniques would be difficult, I would assume. So there's that. And yeah, you could have two individual attempts to mitigate an attack, but if one of them is sufficient, then why do you have the other one? And if none of them are sufficient to protect your system, then it's only really like you have to align the holes in the cheese in order to get an attack through the system.
No, I'm not disputing the I don't know, the foolproofness of the defense, but what I'm saying is that I guess a more useful context would be that RowHammer is a read disturbance error, and read disturbance errors are not common. They're not exclusive to DRAM. So other memories, for example, non-volatile memories or different types of memory technologies in the market also exhibit read disturbance errors. So if you have some sort of mechanism in the memory controller which can theoretically account for read disturbance, then that's a more general purpose solution instead of just focusing on RowHammer.
I mean, if you can come up with a mitigation techniques that's even more broad than only RowHammer, that's of course that might be a good idea. If it takes more energy and area overheads, then you have to weigh up those pros and cons.
Yeah, always there's trade-offs, because in DRAM itself you have ECC, and then you need to add mechanism for. I mean, I guess I agree with you, but it might be really useful to see what is the cost of this across diverse technologies, and but okay, I guess we're on the same page. So thanks.
Mm-hmm. So I guess if no one else has anything to add to the discussion.
I think I have something to add. Like, for example, I would prefer, like, I mean, I'll personally like to solve it in DRAM, because like your agreement between the DRAM manufacturer is that you buy some DRAM chip and you should not get any bit flips, right? So I feel like it's kind of their problem to solve, because they have to provide you chips with any unintentional without any unintentional bit flips, right? Maybe just like not. Maybe we can like look at the question this way as well.
So I guess it should be their problem to make sure that their hardware is not susceptible to RowHammer bit flips.
Yeah, but on the other hand, you have more information on the memory controller side about what accesses do you make, what process is doing those accesses, and yeah, I mean, in the DRAM you have more knowledge about how memory is laid out, but you can get that information at the memory controller as well if you need it.
That's the actual problem, because you can't really do that, because the internal memory layout is not given to you as
if this were to be implemented in real life, I guess we could invent like a protocol which is used for initialization where that data is transmitted. But in this case, we don't even need it, right?
The whole thing about BlockHammer is that it doesn't need the information of how the internal memory is laid out.
Yeah, so my point was just if we were to need that data, there would be a way to get it if it were like an essential solution.
Yes, you would have to make the DRAM manufacturers give up that information, though.
Yeah. But it seems like they already have some data stored in there like we heard in today's first presentation. So I would assume that it wouldn't be too much work to expose additional information.
The question is how much like competitive advantage do you give up when you give the memory layout that you use for your DRAM chips to your competitors? If your DRAM chips are better than the DRAM chips of your competitors might be able to reverse engineer your chip by looking at the memory layout.
Yeah, makes sense. I don't know how big that part is in the efficiency of DRAM chips, if that really makes the difference.
Yes, the only thing that I really know about it is that it is proprietary information, and the DRAM chip manufacturers are not going to give that up so easily.
Yeah, okay, then that might be a problem.
Another thing is you usually only have one memory controller, but you have many DRAM chips in your system. So if you can mitigate the problem in the memory controller, you only have to do it once instead of doing it in every chip you put into the system.
On the other hand, at the memory controller, you have all of the memory requests, but the different chips only get requests which are already directed to them and might cause problems. So you need to handle a lot less requests, and your data structures might be smaller, and thus everything becomes more efficient because you have less false positives. If you already know that the accesses have to be in that chip, in that subarray, in that unit of DRAM.
Yeah. So I guess there are trade-offs to both of those solutions as well.
It's always a trade-off.
Yeah, sure. But I kind of think it's neat to have a solution that works in the memory controller only. So you don't need the DRAM itself.
On the other hand, you might end up with the situation that I think the last paper sort of touched a little bit, which basically said that I think that the DRAM controller implementations of these mitigations are sometimes just not implemented for anything that is consumer grade. And maybe if you buy a server, then you get it, but otherwise no one really bothers, because the only people who care are maybe Microsoft or Google or whoever is operating large data centers.
Yes, that might be the case as well.
Explaining RowHammer to end consumers sounds like
yeah, that sounds like a major challenge. Because it will most likely be more expensive to make a chip that is RowHammer safe compared to just not bothering about it. So if you can sell your RowHammer unsafe chips to consumers, well, you're going to do that. Well, if there's nothing getting added to this discussion, I guess we can wrap it up. I'm gonna thank my mentors for putting up with me and giving me valuable feedback. And thanks for attending my presentation.
Okay, great. Yeah, thanks for the presentation and thanks for the discussion. Since we're already late, I will make relatively few comments. But I think we need solutions all across the board, not just in the memory controller, not just in DRAM. I think it makes sense to research both. I disagree that this is a manufacturer's problem. With the current interfaces, yes, but this is really a technology scaling problem that's affecting everyone, right? It's if we didn't want larger memory chips, then we can solve this problem by going back to some old memory chips that don't have this problem, right? But I think nobody wants that. That makes it everybody's problem, and not just the manufacturers. Because it's now the solution, I think it's good to solve it more openly across the community as opposed to trusting the manufacturers, since that didn't work out very well, as the previous paper showed, right? And I agree with you that I think memory controller-based solutions are actually quite nice if you can completely do it independently in the memory controller, because anyone producing a chip can do it, right, themselves. They don't have to work with any vendor or trust any vendor. They just need to do it on their memory controller. So I think overall, I think cooperation between the vendor and the memory controller is probably a good approach going forward. And I believe the interface to the DRAM needs to change going into the future. We cannot really keep the current interface, because as this problem gets worse, inside DRAM solutions are going to be much, much harder to implement. There was some discussion in the prior paper, right? How many activations are going to trigger? There are two issues basically. Can you keep track of all of the activations that will cause RowHammer flips? Even if you can keep track of them, do you have time to actually do these additional refreshes to the additional rows? And I think both of them become hard, more difficult if we keep the current interface to DRAM, and as RowHammer keeps getting worse. So I think that's an argument against in DRAM solutions. I would say it's easier to solve it in the RowHammer memory controller side, because it's easier to keep track of these things, and you're not bound by some very rigid interface, and you can change the interface, of course, to alleviate the issues. I think with this, I will also recommend people to look at some more recent RowHammer research. I think this was discussed. Let me share my screen quickly. I think you guys had a very good discussion, but I will point you to some of the recent RowHammer research. Are you seeing my screen?
Yes.
Okay, great, thanks. Yeah, so we had this 2 RowHammer papers. This is one, a deeper look into RowHammer sensitivities, experimental analysis of real DRAM chips and implications on future attacks and defenses. This is what was mentioned, what Banu mentioned earlier, on the sensitivity of RowHammer to temperature, aggressor row active time, as well as spatial location of the victim cells. And I think if you understand the problem better, you can develop better solutions. So for example, this paper discusses how to reduce the overhead of BlockHammer, which we just discussed, by taking advantage of the different vulnerabilities of different cells in different locations. And I think this sort of understanding is very good. Right now, BlockHammer treats every cell to be as vulnerable as every other cell. In the worst, basically, it's a worst case analysis-based solution. But if you can actually distinguish the vulnerability of different cells and employ a lighter weight solution for cells that are not as vulnerable, then you can actually reduce the overheads. So I think as we discover, as we understand the problem more, we can also solve the problem better. And then there's this other paper that builds on TRRespass, uncovering in DRAM RowHammer protection mechanisms, a new methodology, custom RowHammer patterns and implications, which basically develops a more rigorous methodology to reverse engineer the TRR mechanisms that are inside the DRAM chips. And it basically shows that essentially all chips that we tested are vulnerable. I'll click on this, but TRRespass is kind of ad hoc, if you will. It's very much fuzzing based. This is a lot more understanding based. Can you basically develop a testing methodology that improves your understanding of what's going on inside the chip? And then can you actually figure out what's going on inside the chip, reverse engineer almost completely, maybe not perfectly, but almost completely. And this paper actually shows, for example, if you look at this table, these are 3 major manufacturers again, you can see that there are different kinds of TRR versions. And you can, some of them are counter based, some of them are sampling based, some of them are mixed, and the capacities are different. And some of them are per bank, Some of them are not per bank, per chip. And there's a ratio of when you initiate these victim row refreshes. You can see it differs. And then how many neighbors each refresh, TRR refresh actually refreshes, it also differs. And then based on this, it builds some attacks that circumvent these mechanisms in a much, much stronger way than TRRespass does. You can see that basically all of the chips are shown to be vulnerable. The HC first values, the RowHammer thresholds are seen here. As you can see, they're actually quite low. And then you can see that more than 70% of the rows are vulnerable in some of the manufacturers. But essentially, all of the chips, you can circumvent the TRR mechanisms in existing chips using a more targeted methodology compared to TRRespass, and you can actually induce a lot of bit flips. So basically, RowHammer research is still going on. That's my, I guess, bigger point. We need to understand the problem better. We need to understand the existing solutions better. I think we kind of understand the vulnerabilities of not trusting, let's say, someone when they say they do it, and understanding what's going on. And also solutions, we need to really develop new solutions. So this is a good time to be really doing this sort of research. And I think hopefully once we solve the problem, we will not get back to it. But I think solution space is also quite interesting because there is no single way of solving the problem. BlockHammer is one nice and interesting ways, but there are certainly other ways as well. Okay, I think I'll stop sharing. There's more to say in this area, but we're way over time. And thanks for the nice discussion. Good, nice presentations. We'll continue next week. Maybe Giray has some comments, and if not, Mohammed can take over.
I don't have comments. Maybe you should take.
Yeah, so yeah, that is the end of today. So thanks so much, Onur, Banu, Philip. I would like to thank their mentors for everything. So the quiz is already available on Moodle. Please don't forget to take it. Thank you so much and take care. Please stay healthy. Bye-bye.